Hello, welcome to Fundamentals of Acoustics. This is the 9th week of this course, and this week till the end of the course what we will be focusing on will be a variety of applications for whatever knowledge we have learnt till so far. So, and this process started happening last week itself. So, last week we had discussed, and actually the week before that we had discussed how to measure impedance of materials which are not known, and then we also discussed about impedance for different types of tubes. And then last week we started discussing about how to model a muffler, and in that particular context we discussed the 3 media problem, because once we understand how to solve the 3 media problem, then we can use that knowledge to design and analyze a muffler. So, all that development of understanding happened last week. So, we had developed the relation which helps us find out transmission loss in a fluid as sound propagates from media 1 to medium 2 to the third media. So, with after doing that, now we are ready to start talking about mufflers. So, that is what we will do in the first part of this week. So, our focus will be mufflers. Now, what is a muffler? So, in a lot of cars or motorcycles you would have seen that from the engine there is a long tube which comes out. So, let us say this is your engine. So, that is your engine, and let us say this is the exhaust area. So, all the exhaust gases, they come out of a pipe, and then you would have seen that then there is another fatter or wider pipe connected to it, and then there is a small pipe. So, the gases flow out. So, this is your atmosphere. So, this entire contraption is called muffler. So, why is it called muffler? Because it muffles. So, the sound which is coming out of engine is extremely loud, because the pressures in the engine are extremely high. So, if those pressures get released into the environment, then that can generate very significant levels of sound. So, what muffler does is it reduces these the amplitude of these pressure fluctuations, such that the sound which you finally hear is not extremely loud. It may still be loud, but it is not extremely loud, so that it can hurt your ears or it can be significantly annoying. So, that is why it is called muffler, because it muffles or suppresses the sound. Another name for this, specifically in our country, is silencer. Okay. So, what we will discuss today is design and analysis of mufflers. Now, there are several types of mufflers. So, the first category of muffler, they are known as reactive mufflers. Reactive mufflers, this is the first category. Several times these reactive mufflers are also called reflection mufflers. Reflection mufflers. And further, in certain cases, they are also known as expansion type mufflers. expansion type mufflers. So, how do they look like? So, typically the shape of these mufflers, it looks like this. So, here the gases enter from the engine, and then you have a wider pipe or a cylinder whose cross sectional area is significantly larger than the inlet port, and then the gases exit out in the atmosphere. And because this cross sectional area A2, let us say this is A1 and this is A3. So, because A2 is larger than A1, the gases expand in it. So, that is why it is known as expansion type muffler, because the gases can expand in it. And then they are known as reactive mufflers or reflection mufflers, because the sound energy when it passes through here, through the muffler, it does not get absorbed by the muffler, but it gets reflected. So, sound energy gets reflected. So, that is why these mufflers are also known as reflection type mufflers, okay. And they are known as reactive because, I mean, either the sound energy has to get reflected or it has to get dissipated. So, it gets reflected if there is reaction occurring or reactance in the system. So, whenever you have reactance in the system, using the electrical analogy or electrical word, then all the energy does not get transmitted outwards. So, that is why they are known as reactive type of mufflers. Now, then there is another category of mufflers, and they are known as absorptive mufflers, or some people also call them dissipative mufflers, or some people call them resistive mufflers. Okay. So, what happens in these type of mufflers? Well, you can have a very simple shape, but the inside lining or the inside surface of this pipe. So, this is the simplest topology for dissipative or absorptive or resistive type of muffler. So, the inside surface of this pipe has a sound absorption lining. So, as sound passes through this, sound gets absorbed by this lining, and that is why it is known as either absorptive muffler or dissipative muffler, because the sound energy as it travels through the pipe, it gets dissipated, it gets converted into heat. And they are known as resistive because the same thing happens in resistor. As energy passes through a resistor, it gets converted into heat. So, that is actually what is happening in these resistive type of mufflers. Now, this is a topology which I have made, which looks extremely simple, but realistic mufflers may have several layers, right, of resistive lining. So, each of these baffles may be lined with some sound absorbing material. Okay. So, as sound passes through it on several surfaces, sound gets absorbed. So, these are absorptive mufflers. Then the third category could be hybrid mufflers. Hybrid mufflers. So, I will just show you. So, in hybrid mufflers we rely on both reactance or reflection of the sound energy as well as absorption. So, in these type of mufflers you can still have a topology like this. So, this will cause reflection, and then you can have sound absorption materials So, you can have even like this. Okay. So, as sound travels through the entire structure, it not only gets reflected back, but whatever is getting out, that also gets absorbed. So, these are hybrid mufflers. So, these are all the several types of mufflers. So, what we will do today is we will start the discussion on expansion type of mufflers, and then we will also briefly cover the resistive type of mufflers in our discussion. So, we will start our discussion by considering expansion mufflers. And the typical geometry we will consider will be of this type. Okay. So, sound air is coming in from this end, it is getting out from here. Let us say this cross sectional area is A1, cross sectional area of the chamber. So, we call this chamber is A2, sectional area here is A3, and let us say that the length of this chamber is L. Okay. So, as air is passing through portion 1, it goes into portion 2 and then goes out from the third portion, it is essentially passing through 3 different media. So, the mathematics of how sound travels through this type of a single chamber expansion muffler is dictated by the 3 media, the solution for the 3 media problem. So, let us say in this portion, so let us call these portions region 1, this is region 2 and this is region 3. So, in region 1 we have density as rho 1 C1, in region 2 we have density and velocity of sound as rho 2 C2, and in region 3 it is rho 3 C3. Now, for purposes of analysis we will make some simplifications, but the basic equation for T, which is the transmission coefficient, that is equal to 4 R13 divided by R13 plus 1 whole square times 1 minus R23 plus 1. So, this is R23 square plus 1, actually excuse me, it is R23 square minus 1, and the other one is R12 square minus 1 sine square K2L divided by R13 plus 1 whole square. Okay. So, that is the transmission coefficient for this kind of a muffler, and if we know the parameters rho 1 C1, rho 2 C2, rho 3 C3, then we can easily compute the transmission ratio for this kind of a muffler. Now, for purposes of our today's analysis, we will make some assumptions which make the relation for T simpler. So, we assume so what do we assume? We assume that A1 equals A2, okay. So, that is one assumption we make, and the other assumption we make is that the ratio of A2 over A1 is equal to M, some number M. So, the cross sectional area A2 divided by cross sectional area of the first section A1 is M, and the first assumption was that A1 equals A3. A1 equals A3. So, with these two sets of assumptions, we will try to compute rho 2 C2, rho 3 C3 in terms of density and speed of sound for the first section. So, to simplify relation for T, we need to find R13, R23 and R12. So, unless we do not know these, we cannot compute the value of T. Okay. So, that is what we do. So, we know so, what do we know from mass conservation? That as air moves from section 1 to 2 and it goes from section 2 to 3, the total amount of mass which is entering in section, getting out of section 1 is equal to the flow in section 2 also. So, rho 1 times A1 times V1 velocity 1 is equal to rho 2 times A2 times velocity 2. Now, please realize that here rho 1 is total density, because typically in acoustical systems we just worry about the change in the density, but here rho represents the total density of fluid, only then this relation will be correct. Okay. And V is the velocity. Now, at the interface of 1 and 2, velocity in section 1 because of continuity has to be same as velocity 2. So, we know that, but V1 equals V2. So, if that is the case, then rho 1 A1 equals rho 2 A2 or rho 2 equals rho 1 times A1 by A2, rho 1 A1. So, rho 2 is equal to, so this gives me rho 1 by m. Well, I mean this velocity, it is moving uniformly in first part, then it is moving with this constant velocity. So, what we do not worry in this case is that there may be some eddy currents which are getting formed here. So, we do not worry about those, we think that the flow is happening uniformly. So, this transformation is okay. So, with that understanding, so this so the density in medium 1 and density in medium 2 is off by this factor. Okay. So, similarly we can say rho 3 equals rho 2 times m. Okay. So, let us call these relations, so let us call this relation 2a, this is 2b. Okay. Now, the other thing is that as fluid is flowing, so there are two phenomena happening. One is that the fluid is flowing from section 1 to section 2 to section 3. So, fluid is flowing like that. The other phenomena is that while fluid is flowing like that, in that fluid sound is also propagating. So, while fluid is flowing like that, in the fluid sound is also propagating, and there is also some DC flow of the fluid or low frequency flow of the fluid. Now, as fluid flows through, it goes from part 1 or section 1 and then it expands into section 2, and then again it gets contracted into section 3, and this expansion happens, it does not happen rapidly, it happens at a slow pace, and then again it also contracts as it goes into the third section. Okay. So, in a overall sense the fluid is expanding and contracting, and it is happening slowly, and because it is happening slowly the overall process in the system is isothermal, because when it expands slowly the temperature goes down and all the extra heat from outside comes in to compensate for the temperature. So, the expansion and contraction of the overall gas when it flows is an isothermal process, but in that, on top of that process sound is travelling, and the propagation of sound is an adiabatic process. So, what we are trying to find out now is the overall pressure of the system in section 1, section 2 and section 3, and that will depend on the isothermal process. So, for an isothermal process we can write P1, which is the total pressure in part 1, times volume is equal to P2 V2, right. So, this gives me P2 is equal to V1 by V2 times P1. Okay. So, here capital V is the volume, capital V is the volume. Now, in 1 second the volume will be proportional to the area. So, this I can write it as P1 times A1 over A2 is equal to P1 over M. Similarly, P3 is equal to P2 times M. So, we can write 4 important relations. So, let us summarize. So, summary. So, what is the summary? P3 equals P2 times M, then P2 equals P1 over M, and rho 3 equals rho 2 times M, and rho 2 equals rho 1 over M. So, what we will do is, going forward we will use these relations to compute these parameters rho 1 C1, rho 2 C2, rho 3 C3. Then from those parameters we will calculate R23, R12 and R13, and then we will find the value of transmission coefficient. So, that part of the thing we will do in our next class, and till then have a great day, and we will meet once again tomorrow. Thank you.